Very happy to introduce the next talk, which joins two topics I find quite interesting. For one thing, machine learning, in particular deep learning, and for the other thing, sustainability and how this can be connected. And if probably the deep learning hype is probably quite enlarged, which Nadja Geisler and Benjamin Hettasch will discuss for us. So let me stop talking here. Let's enjoy this talk. Give a warm welcome to Nadja Geisler and Benjamin Hettasch.
Ja, herzlichen Dank. Hallo erstmal.
Hi.
Schön, dass wir hier sein können. Schön, dass ihr alle hier seid.
Very nice that we can be here, and we're very excited to talk about this on our very first Congress, actually. I'm Nadja, and I just finished my master studies at the TU Darmstadt and will probably start my PhD studies there. I'm doing this for 2 years. I'm Benjamin, and I don't just want to think about how exciting deep learning is and how to apply it, but instead want to talk about its implications. This talk came about by the topic of the 3063 with sustainability, and so we always find exciting to see how machine learning and deep learning interfaces with sustainability. So that's exactly what we were already busy doing, because sustainability is currently, just very topical and exciting. So before we talk about the three different layers of sustainability, let's talk about the societal and environmental impact. Of course, we first have to talk about what actually do we mean by deep learning in these next 45 minutes in this talk. What do you need to know so we can get you along in this talk? How does it work on an intuitive level, not so much on a detailed technical level, and how is it used currently? So when we're talking about deep learning, we primarily mean this construction of neural nets, artificial neural networks. These are machine learning constructs which existed for quite a while, and then interest in them dropped quite a bit because they didn't have the applications one was hoping for, and currently they're actually again hyped and quite a lot of use. So we're talking about lots of connections between different nodes, and they can be connected with different mathematical functions, and each of these only represents a nonlinear application function. And once the weights between these calculations have been trained completely, then each numerical input into this net gives you a specified output, and this might give you classifications, weightings, whatever. Which means for neural nets, the most non-trivial implication is that we need lots of labeled data. So usually, if you're working with neural nets, you need lots and lots of data. They need to be very diverse, should really represent your reality, whatever that means. And like that, you're training the model. So we're seeing quite well in this case, reading from left to right, you're having input data which might be in some format, which we will not discuss today. These are going into the neurons, the nodes, and each of these nodes represents some specific feature. So in image recognition, this might be an edge or a curve. The further you get into the neural net, it will represent more composite and more complex properties. And the trouble is, usually we don't know quite well what the neural net is actually learning. So we find an image classifier which can distinguish dogs and wolves, but we cannot look into the neurons and see, okay, this neuron classifies what the tail looks like. That's not how it works usually. So we have black box models, and in detail, we don't really know what we actually learned in the neural net. So we don't know how the output actually comes from the input. But this is the basis for all systems which we usually talk about when we mean deep learning. So what we have in this case is we use math, lots and lots of data, and use a few tricks from statistics. So we use that when we look at things often enough, then there is some system in them, and if you look at them often enough, you will find the system, so it will generalize. So this uses tricks, which we know for hundreds of years in statistics, and these are applied to get from a heap of data, which we don't really understand, and just use the fact that it's lots of data to generate some generalization and systematization of this data. At least that's the optimistic upshot. So this has, though it's called deep learning, the implication, so it sounds like intelligence and artificial intelligence, so it won't really represent what you think of when you think intelligence. And this here summarizes it quite well. It usually, people usually say the human brain works on habit and conditioning much faster. So we don't usually need to be hit 200 times in the face to learn that we don't like that. But if we show a neural net 200 dogs and 200 wolves, the system will not have learned to distinguish them so far, because then it won't learn from context as the human brain does. So human brain does different things to get a decision.
So we will talk about that in more detail later, but the problem is we just go for mass of data and we cannot reach the, cannot be as precise as we want to. And originally, the plan was to rebuild the brain because we have neurons that fire, and it kind of was the idea, but that's not how neural networks work today. We don't rebuild brains. It was just the original idea. So the interesting part for us is how do we apply this technology? We don't see this technology only in research or in universities, but the technology is very far distributed and we see it everywhere. After this bigger drought we talked about earlier, this technology has quite a high at the moment, and there's really a lot possible at the moment. So there's speech assistants, Siri, Amazon. They need to know how speech recognition and text, and they have to process information from this huge information cluster. But there's also companies like Tesla and Uber, and through them there's like a lot of distribution of autonomous driving, and they have to work with image recognition and stuff like that. And so if you think about that, it's quite easy to see that there's lots of those recommendation systems in everyday life that generate recommendations, like Google and Amazon, and you have like those rankings, and there's also the question, what do I get to see? What does my Facebook page show me? Who gets to see what? And that's not as straightforward as many people think. A lot less known is like systems like systems that do scoring for legal reasons, or face recognition, identifying people. There's also scoring algorithms for some social systems, for example, for insurances. And also application can be happening by those neural networks without any person looking at your application. And these systems, again, work in a way that we don't really understand what's happening. We actually don't understand what's happening. For example, face recognition or those application systems, there will be a 5-second video analyzation, and the system will do quite a lot, like measuring distance between eyes and nose, and then it might find it kind of looks like genetics, and those systems are applied today, and if you actually look at them precisely in more detail and look what they're actually doing, there's quite a lot going on, and there's actually a lot of disadvantages, and they're biased, and it's getting more. And so now we want to talk about scientific
scientific sustainability. So we want to check how relevant is the topic that we do, how relevant are the results that we have for the field of study that we have and for the everyday life of people. So we also questioning, can we reproduce these results at all? Can anyone reading this paper really reproduce the data or even get at the scale of data? So do we have published enough detail, and are the results as valid to make these things possible? So, and can we reuse things that we produce in size, or are they only just a one-trick pony for that one very thing? So also, are they competitive? Are there some systems that are better with less effort? So, and we would like to check with what systems thinking is behind the system. How did we research what is useful or not useful? And finally, what's the validity? What's the impact of the things that we have as a result there? So is it relevant? Is it statistically significant what we produce there? So, well, at this point, let's have a look. So, I mean, some of you might work in science, some from industry, but it doesn't matter. So, how would we wish that science would work? So, very systematically. So, people think about things, they test things, and they see they work, and then it's fine. But in reality, it's very, very common that we have a completely different model behind there. So, there are publications about about how the neural networks work and how to design them, how to make the data flow. People think about some things, they publish it, and other people think, well, that sounds interesting. Let's just take this and build something for my use case, build a new system. So they just take a model that they heard somewhere that just was popular in sciences, and they think, okay, how could we use that? How can we take it? And yes, well, I just put a couple of layers of those behind each other. Let's say just some ballpark number. And now let's use a couple of dimensions for our vector. They just make it up. It sounds plausible. Then they look at the data. You beat the data as long as until they fit into the model. Then you do some numerical computing on them, and finally you put it into the network, and then it's called deep learning because that means now the learning starts. So you push the data into the system, see how it fits, how good is the prediction, and looking at that, then you refit the system, you edit the system, and you try and try again until you do some weighting in the functions, and then you have basically have a made-up model that fits your use case. If the numbers look quite good on the data you put into that, then people say, yeah, well, okay, let's put this into the paper. And they say, okay, for the classification of wolves against dogs, we have this architecture and those data, and these are the numbers. Here you are, this is our great new research result. If the data don't look as good, they say, well, I probably used just the wrong system that someone used. Maybe I have a neural layer too little or wrong dimensions. Well, okay, then I just start again with some arbitrary thing. It's just power and time. And so I let my GPUs run and run and run until they heat up, and I start just start over and see if this time the numbers are right. And well, depending on how this works, you either say, okay, I use it, or I do it again. And in addition, if you look at it, it's not really a scientific, it's not even empiric, it's just try and error, hoping for something good to come out of this. But after that, you can use those beautifications, fairy dust methods that we have in science. And these are hard to track for people who are not insiders. So, for example, you just show the results where the data fit. And then the second data set where the numbers don't fit as well, and they don't work as much, well, I just don't publish those. I just keep them in my drawer. And my numbers that look good, I just publish those. And someone just has to replicate those data and make those numbers look as nice as they are. So, and in many fields of study, this is something that happens if you publish a paper at a prestigious conference with a minimal extension to the state of the art. That's already something people are proud of. But what you also can do is you can just repeat experiments and have the mean of those experiments. You also can use that very experiment where you had the best score and just publish that. And there's other tricks in those. So we already have that process that is misused to get better looking results in a much shorter time and to publish those. And that's what we see a lot in the deep learning field of study. Not in all papers. The fundamental papers are pretty well, but a lot of application papers are actually really, I mean, the way they are made, they don't have any additional value or only relevance to actual research.
This thing is obviously written in a very marketing kind of way to emphasize this a lot. So just imagine there's this field with such pressure and so many reasons for stuff to fail, or on the other hand, to beautify yourself, then you will obviously use this. Obviously, we see it's deep learning is particularly exposed to these tricks. For one thing, so there is research to understand these black box models and understand why they work the way they do. But if you think of these as black box models, it's obviously making it more exposed for such tricks. So the data is processed in some way, and it's going into the system, and then they are post-processed. And then you have to decide what's actually true. Is this true enough? Is this okay to publish in my paper? So what they actually measured will probably not be in the paper. So this is actually where you can fudge a few things to get it into your paper. So because there's a huge demand for experts in this field, it's actually quite easy to get through with methods like this. On the other hand, if you want to get the good jobs, you need to have publications like this, so there's a demand for such publications. And there's lots of low-hanging fruit in this field. So you don't need to have much of good ideas, much of brilliant or new ideas, so you can build something quite easily accessible, and you just happen to be the first one. So you don't need to prove yourself in comparison to anyone else. You just show, I'm the first one to do this with acceptable results. So you're the first person to do this, and then you can publish. So that's why many people want to publish lots of things quickly in these fields. So when we look into how good a system is, which was presented, then it would be nice if we could just reproduce the experiments. That's actually, sadly, not as trivial as you might think. So even if the systems which are used are usually quite standardized and usually open source, that's typically not true for all the details and modifications the people who published the paper have used. This will probably not be true. So you will probably not have access to the evaluation. Typically, you won't have access to the data because this is usually quite precious to have, so you don't want to give it publicly. But that's, on the other hand, not the way science is supposed to work. You can't just give you a system but not give the data. My system is just excellent. I can't give you the data to prove it. In these systems, there's loads of hyperparameters which you firstly usually guess, and then you just do trial and error. And if you don't know these hyperparameters, you have actually no shot at rebuilding this system. You don't know with what separation of the data this has happened, so you don't have a chance how to build the system. But we need all these exact values to build these systems because they are actually quite fragile with regards to these parameters. So if you just change a bit of the things about these chain functions there, you get bad results, and you're not sure if it's because of the original bad publication or if it's you building the wrong thing. Currently, there's a few streams to make this the duty of the research is to publish things along with this, but yeah, there's nothing forcing them to do that, but it's not obligatory to do so. So imagine you want to have a seal to say, my paper is reproducible. Then you have to give all this, which we have on the slide, so code data, hyperparameters, the random initialization, the sequence, and the grouping of data. But you can just not do it. So this is obviously a position where you want to have a discussion because, yeah, it would be good if we had this on all papers. So the effect of all this is we have lots of research which cannot be used by other people. So others have to repeat this research. And additionally, through this effect and the pressure of publish or perish, research will just be published with only minimal optimizations. So this system is better than 0.005% than the reference system, and this will be another paper. So we might wish for having reproducibility everywhere. So the most important thing whenever we're sitting in such publicity, we need to assure reproducibility. But now look, a squirrel.
So that's something that's happening quite often because research, even if they want to publish their source code, they might just not have the time. They haven't cleaned up their code by the timeline because the pressure to publish is so high. It's raising exponential. You have to be faster to be state-of-the-art to bring your own improvements onto the market. So there's the working quality doesn't improve with that. So then I have code that's quite messy, and then there would be much work involved to clean this code up to publish it. And so everything else is more interesting than making this code accessible for everyone. So of course that's not happening everywhere. There's people who actually try to do that and put work into that, but it's quite rare. And so there was research, this reproducibility challenge. There were researchers were asked to look for one paper from 2018 or 2019 and to reproduce all the outcomes. And they were asked to, the authors were asked to publish their code, and then other researchers were asked to reproduce this work and the code. And here the success rate, so there is at least 30% of reproducible work and 54% of somewhat reproducible work. And then there's also the part of the difficulty. So there's like reasonable difficulty, but if it's very difficult to rebuild this code, it might not be worth the effort. And so with at least 20% of the papers, it was really hard to reproduce the outcome, and it was very easy only with a really small percentage. And the question was, do we have a reproducibility crisis in machine learning? And people were asked whether they have a problem with this, if they think there's a problem. And just by doing this research, the asked researchers answered 15% more likely that there is a problem.
Noch ein Beispiel.
Another example.
Das ist jetzt, es gibt tatsächlich inzwischen Paper.
So there are papers actually which are dealing with the question how reproducible are other papers. So they're giving recommendations, or like they're looking for the top-end recommendations. So there were 18 publications on deep learning on big conferences.